Hello! Welcome to this video on observation and correlation. We've, in a previous video, described observation and experimentation as two tools that psychologists and other scientists have available to them when they're conducting their scientific investigations. Today we're going to focus on observation and the type of statistic that goes along with it, the correlational statistic. So let's say a little bit about observational studies to get started. First, we should note that observational studies can be used to disconfirm hypotheses. This is also true of experimental studies, but we will explore experimental studies in a different video. Observational data are often analyzed using correlational statistics, and I use the plural of the word statistics here because there's really a family of correlational statistics that are often used for observational studies. To be clear, these same statistics could also be used in experiments, but we frequently see them in observations, so it's appropriate to introduce them here. The first of these is called the chi-square statistic, and we often use the chi-square statistic when we have nominal data. We're looking for correlations among nominal data sets. Let's take a particular example. Let's assume that you're a political psychologist, and you're interested in the relationship between two variables. One is whether a person is a voter or a non-voter, and the other variable would be whether the person is a parent or not a parent. Now, in both of those cases, we have nominal or qualitative data. Our parent variable has two qualitative levels, parent, non-parent, and our voter variable also has two qualitative levels, and these are voter and non-voter. We want to see if there's an association between those two nominal or categorical variables, and we would use a chi-square statistic in order to tell us about that particular correlation. And this would be a type of observational study. We can take another example and look at another kind of correlational statistic. This is called the Spearman rho. The Spearman rho is often used to look at associations between two variables that happen to have been coded on an ordinal scale, which we also call a rank scale. So let's take an example of that. Let's now pretend that we are sports psychologists, and we want to look at an association between two variables that we've encoded ordinally, that is, some rank data sets. One of the variables happens to be the rank associated with a sprint. So maybe we have 30 people, everybody runs a 100-meter sprint, and we rank order them. This person finished first, that person finished second, that person finished ninth, and so forth. We have rank orders for their sprinting performance. Subsequently, we can take rank orders on another kind of athletic performance that might be of interest to a sports psychologist, maybe their weightlifting rank. So we have everybody lifting weights, we see how much they can lift, and we rank order them from the first right on down the line across the ranks. And we look for an association between the rank associated with weightlifting and the rank associated with sprinting. This would be a kind of observational study that would be appropriate for the Spearman rho. Let's stay with that example, but now we'll just change how we code the data. So we're still interested in sprinting scores and weightlifting scores, but we could encode weightlifting in terms of the total number of pounds or kilograms that the participant is lifting, and we could also encode the racing time or the sprinting time with respect to the number of seconds it takes them to complete, say, 100 meters or something like that. We now have interval or ratio data, and if we have either interval data or ratio data, we can use yet another kind of statistic. This is called the Pearson R, named after Carl Pearson. It also is known very simply as the R statistic. A fun historical note is that Carl Pearson was the founder of this statistic, and Carl Pearson also gave us the chi-square statistic, which we use for nominal data. The Pearson R statistic is used so commonly in psychology and in all other sciences that we're going to spend the next several slides trying to better understand the R statistic. So let's say first that the R statistic ranges between -1 and +1. By the way, that's also true for Spearman's rho. Both of those range between -1 and +1. Values near zero, that's the center of the range, indicate no association or no correlation between the two variables of interest. Values far from zero suggest some kind of strong correlation. That is to say that we could use the values that we have on one of our variables to make better than chance predictions about values on the other variable of interest that we get in our observational study. The R statistic often describes the linear relationship between variables on a scatter plot. And you'll recall that a scatter plot will display pairs of x and y scores. In the next several slides, we'll take a look at many different kinds of scatter plots. So here, we'll stay with our example that we had earlier. We'll pretend that we have weightlifting scores on the x-axis, and we have sprinting scores on the y-axis. And we'll pretend, again, that we have interval or ratio data so that we can use the R statistic as an appropriate statistic for these observational data. So here's weightlifting, and here is sprinting. You'll see that we have lots of different patterns shown here, and every one of them has an R statistic associated with it. Let's zoom in on a couple of them first. Let's take a look at this upper left corner, and we see a very strong correlation because we have an R value that has departed very, very far from 0. In fact, as far as you can get. Here we see that we have 3 data points, and the best fitting straight line, because the R value tells us about the linear relationship, is touching every one of those points. Every datum, which is the singular version of the word data, falls exactly on that line. We have a perfectly negative correlation. And this could occur by chance, but it is unlikely that it would occur by chance. It would occur by chance less than 5 times out of 100. So here's our p-value. The probability of this pattern occurring by chance, relatively unlikely. We have a statistically significant trend here. It happens to be a negative trend. Notice that the R value carries information about the slope of the best fitting linear function or linear trend line. We can contrast this with its polar opposite on the other extreme. We have an R of positive 1, and now we happen to have 5 data points. And in this particular graph, the slope is upward, so it's a positive R value. Once again, though, every datum is exactly on the line. That doesn't usually happen for real data sets, but it makes a nice illustration here. This is unlikely to happen by chance, and we see again that the p-value is less than 0.05. Here and here, we have some more intermediate R values. And over here, interestingly, we have a very, very weak correlation. The green trend line is not shown here, but it gives us the chance to imagine what it would be. And because the pattern is neither clearly positive nor negative, the best fitting trend line is probably going to be a horizontal line, which would have an R value of 0. And that's the kind of pattern that we would expect just by random chance, if there were no association between the x-axis variable, which was weightlifting in this scenario, and the y-axis variable, which is sprinting in this scenario. If it were the case, if there were no association, we'd expect an R value of 0. The best fitting line would be horizontal, neither positive nor negative. Let's move on to some other really interesting cases of the R statistic and look at a whole bunch of scatter plots. This is a busy slide. I'll call your attention to this top row first. Let's begin in the upper left-hand corner, and we can see that we have lots of little individual data points. And every one of those is right on this best fitting line. And because they're all perfectly on the best fitting line, the R value is 1. Here we have a case that's almost as good as this one. That is to say that these data points are falling just ever so slightly off of their best fitting line. It's enough, though, to move the R value from the perfect positive 1 to something a little bit off of 1. We'll call it 0.8. As we move over one more time, we can see that now this oval shape is beginning to become a little bit more circular. Still, though, there's a slight upward trend, and we get a positive 0.4. Here we have almost a perfectly circular cloud of dots. The best fitting line would be right here, which is a horizontal line, neither positive nor negative. We'd have a 0. And then we have, along these 3 instances of, again, the emergence of something like an ellipse, a better ellipse, and then the ellipse shrinks down to a perfectly negative correlation as we see here. So a nice span of R values here, and the pictures are really quite clear. Let's now look at some other slightly more ambiguous cases. In this row, we have 3 items on the left that all have an R value of positive 1. And that's because every datum falls on a straight line that is non-zero in slope. Okay, and they're all positively sloped. Notice, though, that they differ from each other in slope. They're all positive, but this one's relatively steep, this one's a little bit more modest, and this one is quite a bit modest, but it isn't perfectly flat. There's some variability in the y-scores here, and they seem to line up very linearly with the x variability. That is, we have some vertical expanse and some horizontal expanse in our data set. Same thing is true, we'll go to the other extreme, 3 negative 1s over here, and some of them are steeper than others, but they're all perfectly on their line. What's really interesting is the center case, which you'll notice does not have a number. Now, why does it not have a number? The reason it doesn't have a number is we really can't compute the R statistic here because this is undefined. Why is it undefined? Because there is absolutely no variability in the Y scores. Let's try to unpack that just a little bit more. When we're talking about a correlation, we're really looking at the association between the variability in the X variable and the variability in the Y variable. But in this particular data set, there's no variation whatsoever on the vertical dimension. It's perfectly flat. So for this reason, it doesn't make sense to ask the question whether there is variability on the X that is associated with variability on the Y. There is no variability on the Y-axis here, so this is actually undefined. Now, if we drop down to this row, we see another really interesting phenomena. All of these would have best-fitting lines that are perfectly horizontal. They all have variability in the x-axis, and they all have variability in the y-axis. So we actually can compute an R statistic in each of these cases. But here's the central point about the bottom line. These are all very, very different-looking patterns of data, and yet they all map onto exactly the same R value, which happens to be 0. We would have a best-fitting flat line. So this raises an interesting point. We have a many-to-one mapping between the different kinds of patterns we can see and the R value associated with those patterns. All of these generate an R value of 0. Let's take another example. Here we're back to some smaller data sets. There are 11 data points in every one of these 4 graphs. Interestingly, every one of them has the same slope on their best-fitting blue line. And the correlation in all cases turns out to be 0.816. Despite that, you might notice that we have relatively distinct patterns in each of our 4 panels. Over here, we have a relatively straightforward data set where you can see something like a trend going upward here, but there's some scatter, or as we say, noise around that trend line. Over here, the 11 data points are really quite orderly, but they're relatively curvilinear. And we fit a straight line to a curvilinear trend that it was emerging in our data set. That's probably not a really good idea, and this is why it's important to plot the data points in a scatter plot. So we can see that even though this and this and this and this all map to an R value of 0.816, we see really quite distinct types of patterns happening across the 4 panels. Okay, let's return now to understand a little bit about how the R statistic can be used to determine different kinds of things, including reliability. That is, the repeatability of a measure. The R statistic, when strong, can tell us, for example, that we have very high levels of inter-rater reliability. This is a very important concept in psychological science and many of the other behavioral sciences. We'll take an example. Let's say that we are rating dancers and we're evaluating their performance, and we have 2 judges who are rating any given dancer's performance. I'll ask you to draw this with me as I make the cursor move on the screen. Imagine that out comes the first dancer, and we have judge 1 giving a score, and we plot that on the y-axis, and we have judge number 2 giving a score, and we plot that on the x-axis. And at the intersection of those 2 responses from our 2 judges, we get a particular score for that dancer. Out comes another dancer, and that dancer gets another pair of scores that we plot on y and x and so forth. If, generally speaking, we get a nice straight line there, we would have inter-rater reliability, and that would be a type of reliability, a type of consistency in our measurement. So the R value can help us with that. If we have R values close to 0, we have relatively poor inter-rater reliability. We can also think about consistency across measures. So maybe we're going to have just one judge, but maybe that judge makes a measurement at time 1, and that can be our y-axis value. And that same judge measures the same dancer at time 2, that'll be our x-axis value. And that same judge would be making many, many observations at time 1 and time 2 for many, many different dancers. And again, if we have a nice straight line, we would have consistency across those measures. This would be an indication of reliability. So the R statistic is really very helpful because it can tell us about the reliability of our instruments. It can also tell us about at least one type of validity. And we've talked about reliability and validity in another video. Here we're going to focus on how the R statistic can inform us about internal validity, which you might remember is the extent to which we are measuring what we want to measure. Strong positive R values between our measure and a previously established measure of the same variable indicates that we are measuring what we want to measure. That is, it gives us an indication that we have strong internal validity. Let's take an example. Let's assume that we are personality psychologists, and we're interested in measuring extroversion. Let's assume further that we want to develop our own survey for measuring extroversion, and we want to establish the internal validity of our survey for extroversion using the R statistic. What we can do is look in the literature and see if we can find a well-validated and reliable measure of extroversion, and we can have people complete that extroversion scale, and we get scores, and we can line those scores up on the y-axis. Then we bring out our new measure that we hope is a reliable and valid measure of extroversion, and we can score the same people using our survey. And we'd plot those on the x-axis, and the intersection of those will give us a nice scatter plot. To the extent that we get strong positive R values, then this would indicate that our new measure of extroversion is generating scores that are very much like this well-established measure, which is on our y-axis. And so this would be one indication of internal validity. Observational studies, though, we should say, have many limitations. One of the limitations is that if an observational study reveals a significant correlation, we can't draw a causal inference. And there are a couple of reasons why. One is the so-called third variable problem. Some other or third variable might be driving the correlation between the two observed variables. Let's take an example. It might be the case that we can show that we have a statistically significant correlation between the number of traffic lights in a city and the number of murders in that city. Okay, so the number of traffic lights, maybe when low, is associated with relatively low numbers of murders. And then also, when we have high numbers of traffic lights in a city, we have high numbers of murders in that city. Okay, so there's a positive correlation. It might be a very strong, a statistically significant correlation. But we ought not fool ourselves into thinking that there's a causal relationship between the number of traffic lights and the number of murders in a city. There might be some third variable that's accounting for that statistically significant correlation. And that third variable might be something like the population of the city. So you can imagine a very, very large city will have a lot of traffic lights. It will also have a greater number of murders. A smaller city will have fewer murders because it has a smaller population. It will correspondingly have fewer traffic lights. So there can be a very, very strong correlation there, but this tells us nothing about causation. There's another possibility. Even if the two variables are causally related, the direction of causation can be uncertain, even if we have a very strong statistically significant correlation between those two variables. We'll take a couple of examples. Let's assume that we've made an observation about a particular couple. It's a married couple. They've been married a long time. It's a husband and wife. And we happen to notice that he's really quite hard of hearing. We also notice in our observation that she has a very, very loud voice. So he's nearly deaf and she's very, very loud. Now, there might be a causal relationship there. One possibility is that she speaks loudly because he's hard of hearing. A different possibility is that he is hard of hearing because she speaks very loudly. That is, over decades of living together and her loud acoustic energy, maybe that's actually caused the hearing impairment. As you and I come onto the scene with our observational study, we see that there's an association here, but we don't know about the direction of causation. The direction of causation is uncertain. Sometimes we say the direction of causation is ambiguous. Okay, let's now move on to the final idea, and maybe the most important idea. It's a good one to end on. This is really the intro psychology mantra. If you learn nothing else from Introduction to Psychology, we hope that you'll learn this. Correlation does not imply causation. Say it with me. Correlation does not imply causation. Thanks for listening.